Today we're going to be talking about valence electrons and bonding. And we are going to cover quite a few different topics here, mostly things that will help support you in this new module that we are entering right now. All about bonding and naming compounds. So we're going to start off here, once I figure out how to manage all my technology, with a little warm-up question. I will say that next week we do not have a virtual session. I will be attending a professional development, and the week of Thanksgiving we will not have an official session. I am going to open up some opportunities to meet one-on-one with me if you need to, right? That way you can start planning if you're super behind or you need help on something in particular. So I will be sending an email about that for later on. That way, if you do need a one-on-one meeting, we can do that the week of Thanksgiving and get you ready to go. Today, we're going to identify the relationship between valence electrons and bonding. We're going to identify the relationship between electronegativity and bonding, and we're going to draw we're not necessarily going to do in this session, but that is something that you will be seeing / doing in some of the assignments for Module 3, I believe we're in now. So warm-up question, going back to something that we covered a few virtual sessions ago, electron configuration. So take a moment right now to write out the electron configuration for aluminum. And you may need a periodic table to do this, right? So don't be afraid to open one up, or if you have one printed out, get that out in front of you. I'm going to ask that you not post your answer in the chat yet, right? So that everyone can have an opportunity to do this. So we're going to spend a minute and a half right now figuring out the electron configuration of aluminum. And if you have figured that out and you would like to post your answer in the chat, you may. I know a few of you are probably waiting anxiously. If you're not sure, keep working, right? We're going to go over it in just a few moments here. Oops. Ooh, I love that Oliver opted to do the noble gas shortcut. Totally allowed. Love it. We've also got some great answers here from Michelle and from Logan. Michelle, I'm guessing you also did the noble gas shortcut, but don't forget that you have to include the brackets with that noble gas to tell us where you started, right? So that we know exactly where to look. So if you're still working or you're not quite sure how to do this, we're going to go over it really quickly. First thing first, you need a periodic table. Second thing is you need to locate aluminum. Aluminum happens to be number 13, located right here in our third period. So to start our electron configuration, if you took the shortcut method and you started with neon, totally doable, but just in case you didn't, let's start from the beginning. Right, we should have 1s2, that's true. Our first shell is completely full. 2s2, also true. 2p6 would take us all the way to neon. And then everyone got this last part here, which is 3p2, or excuse me, 3s2 and 3p1. We only have one electron in that third p orbital shell. Great, so I'm really proud of you guys. You seem to have gotten this really quickly. I will say, in all my years of teaching this in chemistry, you guys have gotten this concept pretty quickly, so you should be very proud of yourselves for that. So again, if you're not sure how to do that, right, and you're watching this recording and you weren't here live, there are other videos and virtual sessions on that topic, so go back and watch them. So today we're going to talk about valence electrons, Lewis dot structures, right? I'm going to kind of give you some supplementary information to the learning that you are doing in Canvas already, because they do have a lot of detail there, a lot of examples. So I'm not going to go through all of that necessarily. I want to give you guys some supplementary information here and some key ideas. So the first key idea that you definitely want to know is what a valence electron is, which I know we've kind of gone over it again, but can someone remind us either in the chat or speaking out loud, what is a valence electron? Thank you, Oliver. The electrons in the outermost shell of an atom, right? And particularly, these are the electrons that are involved in bonding, right? So an atom could have 400 electrons, not possible, but pretend it did. We don't care about any of them except the ones involved in bonding when we're talking about bonding, right? Because most of those electrons are close to the nucleus. They're just circling around. They're involved in energy levels, right? They're involved in electron configurations, but not necessarily the bonding. So for most of the elements that we will deal with, there are 8 valence electrons in an outer shell. Now, when you get into higher electron numbers, there are some different rules there, right? So that's not necessarily true for every single element, because I know Logan is going to find one here in a second that he's going to tell me that I'm going to say, nope, doesn't work for that one. But most of the elements that you encounter in the class, 8 electrons are going to be how many electrons are in the outer shell of an atom. So in this case, what will elements or atoms do here, right? They want to get to 8. So they're going to lose electrons, gain electrons, or even share electrons to have a full shell. And why, right? Of course, we always want to think about these why questions, but really, we're lowering potential energy. When electrons have a full shell, right, it lowers the potential energy of the atom and actually makes it more stable. So really, we're trying to look for stability here. Now, here's a little picture of the main valence electrons, the number of valence electrons that we see, which happen to be per group. So in group 1, all of these elements will have 1 valence electron. In group 2, 2. In group 3, group 4, group 5, group 6, group 7, group 8, right? Pretty self-explanatory. And what you see here are Lewis dot structures, which is the dots representing an electron for that particular atom. It's going to be pretty similar to electron configurations, which is you'll notice electrons don't pair until they have to. So when we look at an element, for example, carbon, with 4 electrons, right, then all 4 of the electrons we draw as their own individual pair at first, and then they start pairing up as we have more than 4. If they want to get to 8 electrons, what does that mean for D elements? So, see, I knew, Logan, I could just tell that you were going to ask me a complex question about this. Notice which elements are missing from this periodic table. Metals, right? These metals in the middle of the periodic table are missing here because those are the exact elements really that I was kind of mentioning before. If we look on a full periodic table, right, we see all of these elements, which Logan is referring to as the elements in the D section of the periodic table, right? They have a D level of electrons in terms of their electron configuration. Well, metals are very complicated. They do not follow the normal rules. They can have different valence based on different situations. For example, iron sometimes can have 2 valence electrons, sometimes it can have 3 valence electrons, sometimes it can have 1 valence electron, right? So how do you know? Well, you become an expert chemist and then you just know, right? So a lot of these situations you'll find out as we go. You'll see situations where you go, oh, iron can be 2 or 3. Oh, nickel can be 2 or 3. Oh, copper can be this, right? So you'll actually kind of learn based on the ones that you actually interact with. And we'll see some examples later on of naming. Some names of molecules will actually tell you the valence of the metal. So you might see like iron 3. Iron 3 means iron with a valence of 3. Yeah, so it's a good question, Logan. Is it a majority rule that they're not following, or is it a minor one? Well, they're all sort of breaking the rules in different ways. So I think that's what makes it complicated, is that usually you don't discover the valence or study the valence of metals until much more advanced chemistry. Metals also do this weird thing where they sort of just release electrons and create a sheet of electrons that's just floating sort of outside of their atom, which is also a weird thing that not all elements do. But for this class, for our intents and purposes, we really want to look at the valence for electrons in groups 1, 2, 3, 4, 5, 6, 7, and 8, where it's pretty simple, right? We're going to start with the simplest, and we'll leave the metals for future. So just keep in mind that metals in the middle of the periodic table, right, not groups 1 and 2 metals, but other metals, they don't follow these rules necessarily, right? Sometimes they do, sometimes they don't. It's pretty complicated. But really, when you have your periodic table, I would label these 1, 2, 3, 4, 5, 6, 7, 8 in case you didn't already know that, right? And I would save this picture or add it to your notes so that you have a visual of what these Lewis dot structures look like. I'm not going to spend a ton of time on them because they're just another way to represent valence electrons. And again, it follows the same kind of concept as electron configuration. Electrons don't pair unless they have to, something that we're already familiar with. So a bonding shortcut, you guys know I love shortcuts, especially in this class. Some of you may have already encountered this in the lesson, by the way, so we're going to go through it pretty quickly. But really, a bonding shortcut is that you can write the charge that the element would have with no bonding, right? Meaning basically how many electrons short it is of having a full shell. And then you can switch the numbers and write them as a subscript. Now, does this work perfectly in every situation? Sadly, no, but it works in most situations. So here's an example, right? How would hydrogen and oxygen bond? Well, we probably already know, right? Because you think, well, it would make water, right? Or it could make other compounds. But really, if I'm just asking you what's one compound that could be made here, or what is an example of a compound that could be made here with single bonds, right? Keeping it simple. Really what we would think is, well, hydrogen would have a charge of +1 if it gets no other electrons in its valence shell, right? Why? Because it has 1 as its valence electron, meaning it has 1 electron and it's missing 7, right? And actually for hydrogen, it's really only missing 1. But it's missing electrons, right? Oxygen, on the other hand, has a valence of 6 electrons. Oxygen is missing 2 electrons. So really, this kind of is a visual that you need on the periodic table. Where is the element? If it's on the left side of the periodic table, it's going to be positively charged as an ion. If it's on the right side of the periodic table, it's going to be negatively charged as an ion. So really, we're thinking, what would these elements do if they were ions by themselves? Now, this is only one way to think about this, by the way. There's other ways to do this. Regardless, once you have that identified, right, the hydrogen would be a +1 if it was an ion, oxygen would be a -2 if it was an ion. Then we can switch the numbers and write them as subscripts, which is kind of hard to do on the computer. So you guys will always see my notation sort of looks like a straight line. You're welcome to do that as well. If you do want to go through and put subscripts for every single situation, that's also fine, but I won't take points off if you don't do that. So in this case, we would have H and O. We would flip those charge ion numbers so that we end up getting a 2 underneath our H and a 1 underneath our O, right? Obviously, you don't need to write the 1, it's implied. So we would end up getting H2O as a possible bond here. Now, if you're really familiar with chemistry, you know that hydrogen and oxygen bond in many other ways, right? For example, H2O2, hydrogen peroxide. I believe someone made a joke about that in one of the previous sessions, right? That involves a different setup of bonding, but it still exists and still works. Some of these things you're going to sort of learn as we go, so don't feel overwhelmed, right? The reason I know so much is because I've seen so much at this point in chemistry. Right? That's really one of the big things. It's sort of like learning a language. You got to keep seeing stuff. So let's try one more example. Let's say that we want to use barium and iodine, or yes. I'm like thinking which elements am I even using here? So if we go to the periodic table, And we find these, right? We see barium down here, number 56. It is in the second column. If barium was an ion by itself, it would have a charge of +2, right? It has two extra, or excuse me, it needs 2 electrons essentially. Iodine, on the other hand, is in group 7. It would have a charge of -1. So if we go back to our PowerPoint, we will see that I wrote that out already. And if you flip your numbers and write them as a subscript, then you would get BAI and then the 2 as a subscript. Now, another thing that you can do here is you can think about Lewis dot structures. Because I know this flipping thing, for some people, it's like, yes, this is easy. Other people are like, what are you talking about? You can always do a Lewis dot structure, right? Which would be where you would actually draw your valence electrons. For example, you would draw 2 valence electrons on barium, and on iodine, you would draw 7. Oops. And if you ask yourself, how could these things bond, right? It gets kind of complicated because you notice, well, we're going to need 2 iodines for every single barium that we have. Because one of these electrons from barium can attach, oh, whoops, I forgot I wasn't in a drawing here. I was trying to draw a circle into a line, did not work. One of these electrons from barium can come over here to this iodine, but we have another electron left. So we would actually need another iodine atom here for this to actually completely bond. Now, these are single bonds that we're talking about. We're talking about like the most basic situations here. As we know from our own chemistry experience so far, right? Chemistry is never simple. So of course, a lot of elements don't bond beautifully and easily like this. So I want you guys to try, let's see, I want you to choose one of these to do. Just in honor of our time here, since we're already about 15 minutes in. So choose to either figure out how magnesium and phosphorus would bond or how potassium and sulfur would bond. So hopefully we get people selecting both of those options, right? But whatever one speaks to you, I want you to pick one. Look at your periodic table, see if you can figure out how they would bond. I'm even going to put, well, actually, I hope you wrote it down. Write it down if you need to, magnesium and phosphorus or potassium and sulfur, because I got to look at the periodic table too. Okay, we've got a lot of people writing stuff in the chat. I love how in chemistry, the chat just looks like complete nonsense, right? I just see like Mg3P2, SK2, right? Which is just funny to look at because if you weren't in this class, you would go, what is this? But great, you guys did that super quickly, right? So Logan and Catherine both picked the magnesium and phosphorus situation, right? Magnesium would be an ion of +2. Phosphorus would be an ion of -3. We've switched those two numbers to get Mg3P2. That is correct. In terms of potassium and sulfur, right, we would get 2 potassiums for every sulfur, right? That's true. And something I want to point out is you guys wrote SK2. This is going to sound weird, but you actually would write K2S. So metals generally come first when you write out a formula. So even though it would, you in your mind think, well, there's 2 potassiums, I should put them at the end, right? Usually metals come first. I say usually. So again, that's like for magnesium. Magnesium came first. Same thing with water. Hydrogen comes first. Usually things on the left side of the periodic table come first when you're writing out the name of something. Now, is it the same thing? Of course it is, right? Oh, and there's Vitali. Glad to see you participating too. Okay, so moving on. You guys seem to have gotten that All right. Type a 1 in the chat if you've already gone through. Yes, that's true, Logan. Even if it's heavier, it doesn't matter. Usually the left comes first. There are situations where that's not true. You will learn about them. Type a 1 in the chat if you've already done the lesson on bonding and you feel like you've got that down pretty well. I want to see if anyone's done it yet. Logan's done the bonding lesson. Anyone else done that one already? Because if not, it's going to be pretty easy for you to do now. So we're going to just go through types of bonds. Again, this is going to be diving into the shallow end of the pool, and we're going to keep swimming deeper and deeper as we go through this course. But really, a lot of this might be review for you, especially if you paid attention in earlier science classes. So we have many different types of bonds, right? We have covalent bonds, ionic bonds, metallic bonds, different types of covalent bonds. I wanted to write these definitions out for you so that you could see sort of the similarities and differences, right? Covalent bonds are actually the most common type of bond. That's most bonds that you see. Now, these are harder to actually figure out because electrons are shared, right? So when electrons are shared, it can be kind of hard to see exactly how the bond is working. A good example of this is carbon dioxide, right? Which you are exhaling right now. As you listen to this lesson, carbon and oxygen are covalently bonded. Polar covalent bonds means there's an unequal sharing, right? This means that one element is actually taking more time with the electrons. So it's based on electronegativity, which is something we'll talk about in a second. Really, electronegative atoms attract electrons very easily. They're pulling them towards themselves at all times, and other elements can't compete with that, right? A good example of a polar covalent bond is water. The hydrogens don't stand a chance next to the oxygens to hold on to electrons. Of course, they get a little bit of time with them, but it's mostly oxygen. Ionic bonds are the easiest ones to identify because in that case, you actually end up getting two ions that then bond together, which is basically what we were just doing, right? When we were figuring out the types of bonds, we were actually figuring out ionic bonds. Same thing doesn't necessarily work for covalent bonds to do the ion charge, flip the sign, or flip the numbers, excuse me. Doesn't work as beautifully for covalent, unfortunately. But any kind of salt, everything that we just created in those practice questions was technically a salt. So salts are really commonly seen. You'll notice you'll be able to recognize them almost immediately. If you see any element, from columns 1 or 2, right? So anything from your alkali earth metals or your alkaline earth metals, most likely it is in a salt. Most likely. They form salts very easily, right? And again, ionic bonds are only going to be between the extremes of the periodic table. So something on the left side and something on the right side together can make an ionic bond. If you have two elements that are close to each other, like chlorine and fluorine, there's no way that they would ever ionic bond. Again, that's a general rule. Conveniently, the periodic table is organized that way. So if you see two elements on an extreme side, you can do what we just did. Find the ion charge, flip the number, write it as a subscript, and you now have your bonding. If you see something like oxygen and sulfur and you want to find out how they bond, well, you might have to draw a Lewis dot structure. You might have to do a little bit of experimenting to figure out exactly how that works. And then metallic bonds, as I already mentioned, these are bonds with metals, where metals sort of just donate electrons to this big sheet, and they can sort of use that as a way to interact with other materials. We're not really going to talk about them that much in this class. So how does electronegativity affect bonding? Well, if you haven't already discovered the magic of the periodic table, because it is magical, right? The way that it perfectly works out is honestly astonishing to me. But what you want to know is that electronegativity increases as you go diagonally up towards the right. Meaning, fluorine is the most electronegative element. For most of these trends, we pretty much ignore the noble gases, right? As we've already discussed, noble gases don't interact, and basically we ignore them other than when we use them to shortcut our electron configurations. So fluorine is the most electronegative atom. So Logan asks, would 63 be more electronegative or less electronegative than 22? Let's see. 22 is over here, titanium. 63 is, where is it? Down here. So 20, that's a good question. I would say 22 is probably more electronegative. But of course, this is a trend. So Logan's asking a great question here. Usually you'll actually see charts like this when you talk about electronegativity, where chemists have actually given a value to each element, and the height, right, or the amount that the element is coming out of the screen actually represents how electronegative it is. So in this case, fluorine is like dark and the tallest one possible. So fluorine is actually the most electronegative element. Oddly, or maybe not oddly to you, hydrogen is pretty electronegative as well, right? It's almost in the same category as a boron would be. Whereas the rest of group 1 elements, very little electronegativity, and you notice as we go down towards francium, it gets even less. Right, so generally the trend is it's increasing as you go up towards the top right corner. There are, of course, some elements where that doesn't necessarily work, like right in here in the metals, we see quite a surge of electronegativity that sort of decreases again, right? So you can always look up these values, which is something that you'll do in one of the lessons in this module, is you will use electronegativity values to determine information about how atoms will interact. If something is electronegative, it's more likely to take electrons, right? Meaning in a covalent bond, it might not evenly share. Meaning in an ionic bond, it will definitely take electrons from something else, particularly a metal, right? So electronegativity can be super important in finding out how something will behave. For example, fluorine ionic bonds very easily because it's very attractive to electrons. So electrons flock towards fluorine, right, and leave metals all the time, which will then create an ionic bond. So much talking. So examples of ionic bonds, right, like I already kind of said this, but to summarize again, usually form between groups 1 and 2 and group 7, so extreme sides of the periodic table, right? So our alkali and alkaline metals and our halogens are most commonly involved in ionic bonds. Sometimes you get other situations that could be considered ionic, right? It does happen. Here's the Lewis dot structure sort of drawing of what that looks like. Again, we can use the shortcut for ionic bonds. In fact, I should probably go back and add the word ionic onto that slide so that you guys know that that's for ionic bonds, because I don't think I made that very clear. So I will go back and add that in a second. But for magnesium chloride, for example, right, you could have looked on the chart and figured out exactly the shortcut to figure out what the bonding would be, or you can draw the Lewis structure, where you can literally see one electron from magnesium gets donated to chlorine, another electron from magnesium gets donated to another chlorine, the chlorines become negatively charged, the magnesium becomes positively charged, and then they attach to each other, right? So that's an ionic bond. It's actually an attraction between positive and negative charge. Same thing is going to happen with sodium and chloride, right? Although it's even easier. They show the single electron in the valence shell of sodium joining the one missing electron from chlorine, and then they become negative and positive, and then they're attracted. So what about krypton difluoride? Would that exist? Is that what you're asking me, Logan? I don't know if that would exist. You can Google it, and if it, okay, so it does exist. So are you asking if that would be ionic? That's a good question. I would say it might be. Where's krypton on the periodic table? Let's see if we can solve this on our own. What number is, oh, it's a noble gas. Oh, duh. Here I am like, where is it on the periodic table? It's a noble gas. Thank you, guys. So then no, it would not be ionic, but that's a strange bonding situation right there. Because Noble gases pretty much never interact. So if they're interacting, right, it's for a very specific situation. I would call that a covalent bond. I could be wrong. You might have to research that, Logan, and let us know. Usually anything that's near each other on the periodic table bonding together will be covalent. And krypton, being a noble gas, is very near to fluorine, right, in terms of distance, essentially. So, other things about bonding. Okay. Covalent bonds, right? This is the most common. This is what you will see in most compounds. Again, not all, right? But most things that we interact with are, in fact, covalent. Electrons are being shared. So the way that you'll see that drawn is you can see that in this case, they just sort of drew electrons from hydrogen in blue, electrons from carbon in red. This pair of electrons is being shared by both the hydrogen and the carbon. Same thing for oxygen, which can bond with itself. 2 pairs of electrons are being shared between an oxygen molecule, which actually means that it would then be a double bond. Same thing over here with CO2, we see a double bond because we see that, or is this, yeah, carbon dioxide. We see 2 double bonds on either side of the carbon because we have 2 pairs of electrons being shared. So for covalent bonds, you probably need to draw a Lewis structure. You may be able to visualize in your mind what's happening, but I would suggest drawing it because you can always confirm. Hi, Kobe. I don't believe you're in chemistry. So if you're waiting for biology, it starts at 2:30. Yeah. Okay. So eventually, as I just sort of stated, we will see lines representing bonds. You may even have already seen this depending on how much chemistry time you spend. But if you see a line drawn between compounds, right, like here's carbon dioxide with lines, those lines represent a bond. So in this case, carbon bonded to oxygen, we see 2 lines, that's a double bond. Over here, we see a carbon bonded to a hydrogen, we see a single bond. In these longer structures, when you don't see anything in these corners, those actually represent carbons. Apparently, there's also krypton tetrafluoride. Wow. See, I didn't even know that was a thing, Logan. Again, right, there's tons of really interesting stuff happening in chemistry that, you know, you wouldn't know unless you ask these kinds of questions or you look. Does that exist? Well, if it does, then find out like how or why, right? Does it only happen at extreme temperatures? That could be a possibility. So you'll see these lines as sort of a shortcut for how bonds can be represented. Another important component to bonds and molecules and naming molecules is these polyatomic ions. These are known ion groups that already have a charge that sort of act as one thing. So some of them that you might have seen already would be like SO4, SO3, CO3, right? Sometimes you'll see these polyatomic ions and they can be a little confusing if you think about them as separate elements versus as a group. So I would take a screenshot of this diagram, look up your own version of it on Google, add it to your notes, print it out, right? Have it available to you because as you start getting into some complicated compounds, a lot of them involve polyatomic ions, right? And if you're not looking at it as an ion, you're looking at it as individual elements, you can end up being wrong about things. You'll also see these in the names, right? Carbonate, chlorite, dichromate, bicarbonate, etc. So in the name itself, you'll actually see these polyatomic ion words. And you guys are lucky. I had to memorize this when I took chemistry. You don't, right? It's available to you. So make sure you have it so you can access it. Another little random tidbit from this is I have only had one question about it this year, but I haven't had a lot of people turn this one in yet. So periodic trends assignment, where you actually are graphing 2 variables to see a trend. A lot of people are really, really confused on this, right? I don't understand why it's such a confusing assignment because it's really simple. It's just graphing. But if you're having a hard time figuring out how to graph it, you can draw it on a piece of paper. Always acceptable, right? Or you can try using Desmos, which I know some of you use in math. I've linked that here if you would like to graph digitally and you couldn't figure out how to do that, right? Really, you're doing this in order to see trends on the periodic table. It's, like I said, it's magical, really is. So here's another summary screen that you should save. Take a screenshot, save it to your notes, find your own version of it, draw your own version of it, whatever you want to do. These are the main periodic trends and how they work in the periodic table. So electron affinity, which is the same thing as electronegativity, that's the one that we mostly talked about today, right? Where it increases as you come towards the top corner here, right? But we also have things like ionization energy, atomic radius. This one might seem slightly confusing. In fact, let's break this one down. I have a little challenge question for you guys, and then we're almost done here. So atomic radius, what does atomic radius mean? Yeah, how wide the atom is, exactly, the radius of the atom, right? So the bigger the atom is, the more electrons we would expect, right? Because we think, well, if we have a lot of energy shells, the atom's just going to keep getting bigger and bigger and bigger. So which atom then would you think? I mean, you kind of already saw that it's not the way that you would think it is, so I should have done this before, but we would think, right, that atoms in the bottom right-hand corner, for example, oganesson, we would think would be the biggest, right? Because it has the most electrons, therefore it's going to have the most energy shells and energy levels. That's what I would think, right? I would think, oh, well, as you go towards the right, atoms get bigger, right? As you go down, atoms get bigger. Well, that's not the case, right? In fact, it's the opposite. Well, somewhat the opposite. As you go down, the atoms do get bigger, but also as you go to the left, the atomic radius gets bigger. Why? Why is the bottom left corner going to have a bigger atomic radius than the bottom right corner? Because of that one loose electron. Okay, so that's a great thought here. Logan's thinking, well, if the valence is 1 and there's one extra electron, maybe that extra electron just really increases the radius size. True, that's a possibility, but let me ask you guys this. What's happening in the nucleus? What charge does the nucleus have? Positive charge. I like that you put a question mark. Yeah, it's positive, and electrons are negatively charged, right? So actually, the more electrons you have, the tighter in the atom gets. Because then you have a stronger positive charge, and the electrons are going to get as close as possible, right? And we talked about how they can use those energy levels to do that. But in this case, right, electrons are going to get as close to the atom as possible, and the more of them there are, the easier it is to do that, which seems a little counterintuitive. So Logan, you're partially right that one valence electron or two valence electrons, right, they're going to actually make the atom like looser in a way where the energy levels are more spread out. And the charge is not going to be as strong in the protons, right, because there's not as many protons as there are as you go towards the right. And so the electrons are actually not going to pull in as tightly in the bottom left corner. Pretty interesting, right? I know a lot of people just memorize that one and don't like think about it, right? But that's why. So it has to do with the amount of electrons and also the positive and negative attraction between the nucleus and the shells. Okay, we've made it to the end. So you are going to do a little exit ticket. This is available for you to turn into Canvas. I will extend the option to research additional compounds if you'd like. right? So Logan, I know you could use krypton tetrafluoride as one of your or compounds to explore here, right, if you'd like to, or you can use one of the ones listed here. But what I want you looking for is which type of bonding is happening. I recommend you try to draw this out, right? How would this look in a bond? Notice SO4, one of those polyatomic ions, right? OH, that's also a polyatomic ion. There's no harm here in actually looking this up. But before you do, I want you to try to figure out, just looking at it, what do you think? Would it be ionic? Would it be covalent? Would it be something else? Are you not sure? What would the bonding look like? Would it be a single bond, a double bond, a triple bond that exists, right? What would happen so that these elements can bond? Now, some of them are super easy, like carbon monoxide, you probably can figure out pretty easily. K2O, you could probably figure out. Na2S, you could probably figure out. And then some of them are a little harder, right? So try to choose at least one that will challenge you. So really, this is an exit ticket for you. You're looking at this just based on what you know from today and what you've known from the lessons. What type of bond is it? And why would that be the type of bond that happens? Try to draw it and then look it up, right? And see how close you were. Because some of these are hard. You'll notice there's some weird patterns too, where you'll go, oh, I didn't realize OH kind of stuck together, right? It's a polyatomic ion, it does that. So this is sort of an exploratory phase. Also look up what some of these things are and what they actually do, because that might surprise you too. And yeah, Logan, you have no idea how krypton tetrafluoride exists. I don't either. I've never heard of that existing. So I'm interested. I hope that you do turn something in. And you can't find anything about its bond. Interesting, right? So yeah, so there are some compounds too that you'll come across in your life that have maybe been made before, but no one can figure out how they were made, right? There's still a lot of mysteries in chemistry. So don't be surprised if you go to a compound's Wikipedia, for example, and it doesn't say anything. And you're like, huh. It may mean that it exists or we think it exists, but we're just not sure. Interesting. Yeah, so I'll be interested to see, Logan, if you could think about how that bonding might work. I would love to know. I'm going to guess it's covalent. That would be my only hint to you. Otherwise, I'm going to send you guys off to do this right now or a little bit later in the day if you'd like. But remember, this is an exploratory phase. How do you think they would bond? Why would that be true? And then what would it look like? The drawing is a challenge option, right? And then look it up. What does it actually look like? All right, so I will not see you guys next week or the week of Thanksgiving, right? Unless you'd like to make an appointment with me. If you'd like to make an appointment with me, please send me an email so I can give you a time slot and we can meet. That meeting could be you're confused on something, you're behind and you need help on how to get caught up, right? You have a question, you want to talk to me about something else, right? Whatever you want to talk about, we can make an appointment for that. So if you would like to meet with me individually, the 20th is the day. All right, otherwise, thank you guys for being here today. I look forward to seeing your exit slips. And thank you to everyone who participated. I actually have it written down that I had every single person say at least one thing today, which is great. All right, so I will see you guys after Thanksgiving, unless you make an appointment with me. Okay, have a great day.